Good afternoon. I'm Kumar, Shaurya, Shankar, and this is my colleague Jiaji. And we are here to discuss our research on robust iterative policy search for acrobatic helicopter flight. Now, following trajectories autonomously using a helicopter is a very interesting applied robotics challenge. And one key benefit of this is that we can devise controllers that can follow trajectories that humans cannot. So, for example, in this case, we are trying to follow a trajectory called a nose-in funnel maneuver, where the helicopter flies a circular trajectory with the nose always pointing towards the center of the circle. So now clearly this is a very challenging task because no matter what kind of system we model, we'll always never be able to encapsulate the entire state information. Even if we do, there will be systemic noise and noise in the sensor data. More importantly, because of the high dimensionality of a state space, it would be very tough to use traditional learning approaches to devise a controller. So we used the reinforcement learning approach to this. We investigated this. And what that involves is that we essentially try to learn a sequence of policies that map from a current state to a control input that subject to minimizing the sum of all the one-step cost functions given a particular system dynamics. So in this case, G is a one-step cost function that is the cost incurred on moving from state xt to state xt plus 1 given the current control input ut. And the current existing approach is ILQR, which approaches this problem by linearizing the dynamics about a target trajectory. And what it does is that it does Taylor expansion of the system dynamics. And so it expresses xt plus 1 as a linear combination of xt and ut. And to evaluate the argument, it performs quadratic value function approximation. So the disadvantages clearly are that if you make any mistake, as you move along the time steps, the error propagates quadratically. And linearizing your dynamics is not really a very good idea.
Okay, how do we fix this? So we propose our Ips Dp algorithm. It works as follows. So suppose you're given some state visit distributions, and imagine a backward dynamic probing process where at time t, and you're given the policies from t plus 1 to the end. So what you do at this time index, you first sample, like let's say n states from this mu-t distribution, and you sample corresponding controls, and you move one step according to the state and control, and you use the cached learn policy starting from t plus 1 to the end. And then you sum over all of the one-step costs, so you get the cost to go. Now you get a collection of cost to go, and you fit a quadratic over it, although you might fit something else, as long as you can solve this argmain fast or analytically, you'll be fine. So if you fit a quadratic, this pi txt will be a linear policy. Why is it good? So basically, first, the mu1 to mu h minus 1 is some distribution that estimated by rolling out a given initial policy, let's say ILQR. So it is actually a meta-algorithm where you just input any initial policy and we improve over it. And second, which is very important, we use the true cost to go by rolling out to the end. So there's no function approximation and there's no quadratic propagation of the error. And third, we use the true dynamics instead of linearization around some point. So there's no error incurred of that. This is our experiment result. So it's basically the helicopter hover for a few period and then do a funnel, which is circle around. And this is sinusoidal saying where the dotted lines are the target trajectory proposed by some human. And the solid lines are our executed trajectory. As you can see, it follows the trajectory pretty accurate. So it's successfully flight. Any questions? Thank you.